Hello and welcome to the AI Research Roundup. I am Alex, and today is May 12th, 2025. Alright, today we are looking at a research paper titled OpenHelix, a short survey, empirical analysis, and open source dual system VLA model for robotic manipulation, which appeared on Hugging Face's trending list just 6 days ago. This paper tackles the need for open resources for dual system vision language action architectures, or VLAs. These VLAs are AI systems for embodied intelligence, essentially AI that interacts with the physical world. They use two parts: a thoughtful system 2, often a large multimodal LLM for reasoning, and a quick system 1, a policy network for actions, aiming to provide an open source model. Building on that overview, this table lays out a comparison of various existing dual system vision language action architectures. It details design choices for System 2, including its model and training, and System 1, showing its policy head, that is the component generating actions, its sensory inputs, which are different modalities like language, visual data, or proprioception, the robot's awareness of its own physical state. It also shows the kind of latent representation, an internal compressed summary of information used, and if the policy head was pre-trained or trained from scratch. This comparison highlights the design landscape the researchers are investigating. Alright, so this next visual really breaks down the core architecture of these dual system vision language action models. We see the MLLM, that thoughtful System 2 on the left, processing inputs like images and language. It then passes a latent vector, that internal summary, to the fast-acting policy System 1 on the right. This policy also takes in more immediate sensory data to decide on an action. Importantly, the diagram points to key design considerations such as how these two systems are integrated and their asynchronous strategy. Basically, how their timing and information exchange are managed. Okay, building on those design considerations, this table specifically looks at the performance of different projector initialization strategies within the Calvin simulation environment. Now, a projector here is a neural network component that essentially bridges the gap, translating the output from the large, multimodal LLM so it can be understood by the policy network. The crucial takeaway here is the impact of pre-alignment, which means training this projector before training the main, large, multimodal LLM. We see that without this pre-alignment, task completion rates plummet to 0, regardless of other settings, underscoring its fundamental importance for the two systems to work together effectively. Okay, and following that insight on projector pre-alignment, this table further compares different ways of using the System 2 model. It shows performance in the Calvin benchmark, highlighting that a large multimodal LLM using prompt tuning, a technique adapting the model by only adjusting small prompt parameters, already outperforms a standard LLM. Crucially, when an auxiliary task, an additional learning objective, is introduced to train this large multimodal LLM to predict action information, task completion rates improve even more. This enhanced performance suggests the auxiliary task helps the large multimodal LLM better integrate its visual and textual understanding for action. So, this figure really details their OpenHelix framework. Part A on the left is the high-level, large, multimodal LLM. It uses a vision encoder, which processes images, and a tokenizer, breaking down text instructions, to feed the large language model. Remember that auxiliary task? It is here, training the model to predict action details, enhancing its reasoning. Then, Part B shows the low-level policy. It receives a projected goal from the large multimodal LLM, combining it with current 3D scene information and proprioception, using attention mechanisms to generate the precise action. Okay, so building on that OpenHelix framework, this table shows concrete performance. We are looking at the Calvin benchmark, including the more challenging Calvin E for enriched instructions, comparing methods by task completion rates. Using the large multimodal LLM with prompt tuning and a pre-trained policy, that is, policy P, improves over a policy-only approach. Then, introducing that auxiliary task, AUX, gives another significant boost, especially for completing multiple tasks. And interestingly, varying the asynchronous inference delay, basically how often System 2 updates. System 1 here at 10 or 60 step intervals, has a surprisingly small impact. So, to wrap up our look at OpenHelix, this work really underscores how crucial specific design choices are for these dual system architectures. We have seen that properly integrating the two systems, for example, through projector pre-alignment and enhancing the large multimodal LLM's understanding with an auxiliary task, leads to significant performance gains. These Vision Language Action Models, or VLAs, which combine visual understanding, language processing, and action generation, show great promise for robotic manipulation. That is all for this AI Research Roundup. Thanks for tuning in.